topic is about multiple input, multiple output system. Okay. So do you know what is a multiple input, multiple output system? Okay, maybe. Basically, it's just a system where instead of having just one transmitting antenna and one receiving antenna, you have multiple transmitting antennas and multiple receiving antennas. Okay. So the last time we made the example of a communication system where you had a base station and a mobile phone. They were exchanging information. A common example for modeling multiple input MIMO system, it can be, for example, the you know what is digital subscriber line, DSL. It's the broadband technology that you use for having your connection at home. It's it goes over telephone wires. So basically, this works that you have something which is called central office. You have a telephone wire, and then this goes directly to your house. But then, actually, there are many of these wires that come out of this central office where you have wires. So now, the main problem of this system is that you get interference. So basically, you require some service. Okay, this is you require some service from your service provider, and then you may get something which was intended for your neighbor. So you don't want to see what your neighbor asked for, and your neighbor, doesn't want you to see what he asked for. So this is interference. Basically, this is the main problem in multiple input MIMO system. You send a signal from multiple input, it arrives to multiple output. The problem is that at each one of these receivers, you get interference from all the other transmitting signals. Okay? So basically, the main problem in all MIMO systems is trying to get rid of this interference. Now, let's see a very simple example, which is a 2x2 MIMO, which means that you have 2 input and 2 output. So you have here the direct channel between the say first input and the first output, the service provider and you. Then you have the direct channel between the service provider and your neighbor. As always, you have some noise, which is always there, and it will be always there. But then you also get interference. Okay? So this is the interference from input 2 to output 1 and then 1. Okay, now basically, so the signal that you get here is X1 controlled by your channel plus X2T, which is here. I guess this is 1, 2, and this is 2, 1. Plus noise. And then Y2 is X2T controlled, here is the convolution, by X2T plus X1T controlled by X21T plus W. Okay? So basically what you get receiver 1, you get the useful signal. The receiver 2, you get the useful signal. but you get also basis interference plus noise. Okay. So we have again the physical problem. We have a mathematical description of the problem by means of convolution. The immediate next step is to apply some modification in order to make the problem more easy to be solved. Okay. Now, as we said last time, it would be very, very nice to be able to express this in a linear system by means of matrices and vectors. So only convolutions and summations are involved. Both are linear, so this is indeed possible. Now, let's try to do it, because the senior yt, this can be gathered in one vector. And then you know that here you have your multiple input and your multiple output. And then in the middle you have the channel. And this is okay. Y1 is equal to H1 combo with X1 plus H12 combo with X2, right? And then, as always, you have the noise. I mean, we are almost there, but we do not have yet tractable expression. We still have convolution. We want to make it like in a matrix, let's say notation. And to do this, let's first analyze easier example of this. Basically, we assume that the channel is a time sequence, so the channel has several time samples. An easier version of this problem is the so-called memoryless example, which means basically that each one of these is not a sequence, or well, it's a sequence, but it contains only one sample. Okay, it's called instantaneous mixture. This is a convolutive mixture because the input are mixed by means of convolution. And then you have the instantaneous mixture when these are just samples. So in this case, basically, what you have is that your resist signal is one sample. Your channel coefficients are samples, as well as the transmitted signal. Now, again, what we see is that this can be the vector y, right? This can be the matrix H, vector x, and w. So this is, I mean, you will see so many times this equation in this course that you will get sick of it. And again, once you did this, your job is basically done. Because again, you know how to estimate x, which is the signal, given that you have some knowledge about the channel H, okay? Because basically, as always, okay? So again, you have physical problem, mathematical problem, you reshape things a little bit, you end up with a linear model, and once you have this, you just invert it, and you retrieve the information that has been transmitted to both, like both the users. Basically, what you are doing by this, you are getting rid of interference, okay? Because what you will get is exactly the two signals transmitted separate from each other. So only X1. S1 and S2, starting from their mixture. Okay? Is it clear so far? Now, what happens if instead of having convolutive mixture, we have, instead of having this instantaneous mixture, we have a convolutive system? What it happens is that we take, let me just install this. I mean, it turns out that, of course, you are still able to make a model like this, which is invertible. And you also know how to do it, because you know that if, for example, you know this channel here, but you don't know the signal transmitted, you know that this is a convolution, so this is a linear operation which can be modeled by a convolution matrix x11, right? And you can do exactly the same with the second term, which is x12, x2. This becomes y1, w1, vector y2, so basically what you're doing, you're taking the information that you know, which is the channel. We assume we have previously estimated the channel, so we know the channel. And then we build all this model, filling up the convolutional matrices with the samples from that channel, okay? Now, once you have this, I will say that it's again done, because you can say that you can start y1 in the vector. This is a column vector. This is again another column vector. You put one on top of the other. H11, H12, H21, H22, X1, X2. And again, this is okay. I mean, it's basically the same. You know how to pass from a convolution in this form to a convolution in matrix notation. So you just again build this model. This is exactly the same, okay? Y1, H11 by X1 there, plus H12, S2, plus noise, right? And the same for the second signal. I mean, imagine that instead of having the channel, you have the signal, which is the training signal, but you don't have the channel. How does this model change? Like imagine that here, now, you have this, but you want to estimate the other one, the channel, right? This is, yes, basically what you do, you just, instead of writing this, you make it just by filling your convolutional matrix with the training signal that you have, the information that you know, and then. And this is all the others. This is exactly what we have seen the last time. Now, basically, tomorrow I will give you 3 files, 3 audio files, 3 sounds, and these 3 sounds, each one of these 3 sounds corresponds to each of the output of a minus system. Okay, so basically you will listen to the sound and you will hear 3 sounds, one on top of the other. Okay, and these 3 sounds have been mixed by a matrix like this. I mean, this is a 2x2 system. That would be a 3x3 system. And then I will give you some hints in order to be able to, estimate this channel and then retrieve and separate all these audio files. Okay, but the main theory behind it is basically this. Now, in order to do this, you will also be asked to estimate some time of delay, but you already know how to do it. And you will be asked in the end to perform some inversion like this. And what you will get in the end are the 3 original sums. Okay? Is this clear? Do you have any question? Okay. Now, if you remember at the beginning of the class, I said this is about like time of delay estimation, minus system, and the third one was dealing with very, very long sequences, like OD5. So this is the last thing that we will basically see today. If this is okay, I will switch to block processing. By the way, do you know how to make a convolution in frequency domain? In Matlab. Have you ever done it? Okay. So basically, you know that there is a very fundamental theorem of signal theory which says that there is an equivalence between doing this operation and do you agree? Okay, so if you make a convolution in time domain, this corresponds to a multiplication in frequency domain. Is this correct? Well, in a discrete world, again, when you have sample signal, this is half correct. Because actually, if you have a product in frequency domain, what you have is cyclic convolution, right? It's a circular convolution in time domain, which is denoted by this. And this is the main problem we will have to deal with, because in general you want to implement this convolution in frequency domain, so the result of your, you want something like this. You have your signal X, you want to convolve it with your signal H, this is NX, this is NH, and what you expect is a Y signal, which is like this, right? But if you make it in frequency domain, that's not what you will get. What you will get is the results of cyclic convolution. So you can think about cyclic convolution as taking the input signal, okay, and consider a periodically extended version of this input signal. So basically assume that it is basically a cyclic convolution because the output of the signal is basically overlapping with the input to the other one, so it's like coming back. And you can think of it as just taking a periodically extended version of the input signal. And then again, you convolve with H of n, and what you get now is this, but part of this, the convolution between this signal is basically overlapping with the second one. That's why it's cyclic. You see, basically what we get, we take what we have here, and this part here is feedback to. Okay, that's why it's cyclic. Okay. So basically, this cyclic convolution, circular convolution, what it does, it gives as output this here. And this is the problem, because if you make this in frequency domain, that's what you will get. You will get that signal where this tail is moved at the beginning, or if you like more, you get this part here. Okay? Now, what can we do in order to get this frequency domain transformation, frequency domain convolution to return you exactly something like this? Okay, so zero padding you said, right? Yeah. So, yes, exactly. What we will do, we will just insert some zeros at the end of the transmitting signal X in such a way that this tail will find only zero of the input sequence so that we can exactly extract that specific portion. So basically, let's see how this modifies. What you do, you take your input X, and in jargon, we say that you zero pad this signal, you add zeros at the end. How many?
At least NX plus NHX severe long.
Okay, so basically, that's what we need, right? So this is NX. You add NH minus 1 samples. And now if you see that if you periodically extend this signal, and you make the convolution with H and N, what you get okay, and you see that now this signal here is exactly this one, okay? So if you want to make it in frequency domain by the FFT function, as your colleague was suggesting, you take the input signal and you have to put some zeros at the end of it in order to make the overall length exactly equal to nx plus nh minus 1, okay? Now, as we saw before, when you make every frequency domain operation in Matlab, what we do, when we say frequency multiplication is an element-wise frequency multiplication, element by element, okay? So what you do, you also have to take the signal H and zero pad this signal up to this length here. Because then otherwise, when you make this element-wise multiplication and the sides of the vector are not the same, yeah, in the previous Matlab version you got an error, now you get something weird. But it's, that's what we need. By the way, if you remember before, I said this thing about Matlab, about making a multiplication by a vector and a column vector, and I said that in the previous version, actually, I was a little bit wrong, because in that case, in the Matlab code, we had column and row vector, okay? So basically, the dimension actually mapped in that previous example. This problem about the new version of Matlab, which, by the way, is not a problem, it's just some choice. It happens when you have like matrices and vector that mismatch. Just a correction to be here. Okay, so we know how to make frequency domain convolution. So you take the two signals, you zero pad both these two signals, you take the Fourier transform, and then you take just the first and y samples of the output signal, okay? Of course, before getting this, you have to come back to the time domain, right? So you make some IFFT, inverse Fourier transform. Okay, this is just an implementation detail that it may be useful if you really have to deal with very, very long sequences. The algorithm that Matlab uses to implement the fast Fourier transform is called Radix2 FFT, and it is extremely optimized if the number of samples of your input vector is a power of 2. Okay? So basically what you can do, instead of padding this up to ny, you can pad it up to, I don't know, the first power of 2, I mean the closest power of 2 this. I don't know, imagine this is 100 samples, so basically you can just go to 128, which is 2 to the power of 7, then you make the Fourier transform of f and h, and then, anyways, in the end, you pick up only the first ny samples, okay? This works and this is efficient. I mean, even if 128 is greater than the actual duration of the signals, if you use this number here, it will be more efficient. I mean, just some comment about this. Okay, but the point is, what happens if you have such a long input sequence X that you are actually not able to do this, okay? So, assume now that the sequence X is incredibly long. You want to convolve it with H. This is X. And this is really, really too long to perform it in one shot. How can you deal with this? How can you make a convolution with such a long sequence? I think we did something similar before, right? So what's the approach?
Divide the sequence, divide the X.
Okay.
In blocks.
In blocks. So I take 1n, let's say m. Okay. And now I perform the convolution between each block and the channel. Okay. Does this work? I mean, does this return me exactly the output of this convolution? No, because again, you make this convolution. In the end, what you get, I mean, if you make this, what you get is actually this overlap. Otherwise, if you make this blockwise, you will get first this one, which is x1 and convolved by h of n, right? From here to here. Then if you take the second one, actually you go from here to here. And you see that basically this portion here is the combination of both these two. So you have basically to overlap and add this stuff here, okay? So what's a possible solution? Well, I mean, it's quite intuitive what you do. Assume that again you have this like, let's say, n samples. What you do, you can just take the first block and you get this, right? Then you take the second one. I mean, you take these and you store these in the vector. Then you take the second one, and what you do, you store it in the vector but starting from this position. And you go on. And you go on, okay? Then, once you have this, you just need to sum up, right, around the vertical dimension. And in the end, what you get is exactly is it okay? So, block by block, and then you sum them up. Now, to make it more efficient, you can also implement these in frequency domain. Okay? It doesn't really matter. Is this clear? Are you convinced that this returns exactly right?
But you sum also the tails.
This is 0, right? Yeah, sure. I mean, that's the main idea here is that is this, okay? Because as we said, this part here is the contribution from the previous convolution and the current one, okay? And they overlap in this region. This is very common in audio signal processing and this kind of applications which involve very, very long sequences. Okay, questions?
And you didn't solve that problem. Did you?
Which one?
The problem of overlapping. You said that you're going to solve this problem by another way.
I mean, what I'm doing instead of taking the whole signal X and convolve it with H, since this is computationally too expensive, what I do, I basically split it into blocks, and then I show you a way to perform this convolution in such a way that in the end, what you get by this block processing is exactly what you would get if you were able to get to process the whole block data together, right? Okay. Same question. Now there is a technical aspect of this, which is important to take into account. And again, this will be more clear when you will deal with frequency estimation and periodogram and these kind of things. But basically, before you said you take the signal, then you take portion of the signal. This is called windowing. It means that it means that you take a window, which is this, and at each interval, you shift your window and you take different portions of the signal. Okay. Now, there is a comment which is important to do about this. So we assume that we take our window, which is a rectangular window, which basically select portion of the signals, and then we shift this, right? Likewise. Now, what we assumed before is that each window takes this joint portion of the signals. Okay, there's another possibility, which is take overlapping portion of the signal. So basically, instead of shifting this by n samples, you may shift this by r sample, which is lower than n. So this is the first thing you have to get. Then you take this, okay? Then you take the other one. I mean, the principle is the same. When you fill your final vector, there will be portion of that vector of that final convolution that are due to the contribution of different, small contributions made blockwise. Now, basically, what we are doing, we are saying that assume that we have a window like this. Okay, this is your W, and which is the window, and this is 1. And what you're doing, you're basically taking this window and shifting it over the signal. Basically, we say that the signal K, which is the K, of this block, is basically equal to the overall signal X multiplied by this window, okay? And the window needs to select that specific portion. So this is a window which is translated by R, where R now is the hop slides, how we're shifting the window step by step, okay? So basically, this is the same signal which is selected by the window. So what we're saying that the overall signal X can be decomposed in a summation of all these signal Xkn. Okay? Which is the overall signal by the window. Okay? Now, let me write it down here. You know that this doesn't doesn't depend on k. Okay, this is the velocity, and we can take it out of the summation. So this is equal to this. Okay? So you see that in order this condition to hold, what we need this summation to be equal to 1. Okay? So basically it means that if you take the first window, which is this is 1, then we assume that we do not overlap the window. So this is the second window. And so on. If you sum them up, okay, what you get, what you need to have it at the end is a constant which is equal to 1. So this allows you to set the amplitude of this to 1 because you are not overlapping these windows, okay? Now, assume that we overlap these windows by 1/2. Okay. Now, okay. You see, okay? Basically you overlap the window by 1/2. Then, when you sum them up, let's assume that we start sum from here to here. What you see is that you sum the contribution of 2 windows at each of these steps. So basically we get again something like this, but the amplitude of this is exactly the double of the amplitude of each individual window. So this tells you, that condition tells you, okay, feel free to overlap the windows, but set the amplitude to 1/2. Okay? Such that when you sum them up, you again get 1. If I remember well, this condition is called constant overlap and end, COLA. Okay? It's, you can find it online, it's very common. And then this condition holds for any window shape. This can be a triangular window, this can be, but the main idea is this one here, okay? You can overlap windows, it doesn't change anything, actually it improves the performance of your convolution. But you need to take in mind that the amplitude of these windows need to fulfill that condition over there, okay?
And the overall sum is 1 in this way.
In this one? Yes. Because if you let me grab the board effect, the side effect.
Yeah, the side effect.
Yeah, side effect. It's an abstraction of like, simulation environments in general. What you sum up is always. So you know how to estimate the delay. You know how to deal with minus signals, and you know how to deal with very long sequences. I think you are ready for tomorrow. Do you have any questions? Okay, so see you tomorrow.